Hi, my name is Ali from Mellanox Technologies, and this presentation is about a new protocol called Ethernet over InfiniBand. So the goal of this protocol is to provide the ability to run Ethernet services on top of InfiniBand network. So this doesn't only include IPv4 and IPv6, but also provides the ability to run any Ethernet application, like, for example, NCSI, a 1Q VLAN protocol, and also it aims to provide the ability to run the management tools such as DHCP and PXE the same way they run over Ethernet. Also, one of the use cases that we want to solve is the virtualization case. So in virtualization, in VMware, KVM, and Zen, there is a vSwitch, and the vSwitch expects to have Ethernet header inside of the packet. So the moment you have the Ethernet header inside the packet, we want to have Ethernet over InfiniBand. So providing solution for Ethernet services and management tools is the main goal of this protocol. So we'll put it this way. Seamless support for Ethernet services and seamless support for Ethernet management tools and utilities. And also the third goal is to have distributed mode, meaning that we want this protocol to be able to run without any central software or hardware manager. So for example, we still need the subnet manager, of course, for the InfiniBand network, but we don't require any hardware support or software support to be as part of a centralized manager to make Ethernet over IP work. So these are the main goals for pushing and designing this protocol. So the first thing that comes in mind is a comparison with the existing solutions. Today we have the IP over IP is widely used in the market, and we have Ethernet. Most of the management tools and protocols are designed on top of Ethernet, and we have in the middle column the Ethernet over InfiniBand solution. So I put here the key differences between the protocols, and obviously the first one is the Ethernet header. So in Ethernet, we have the Ethernet header, of course, existing, presenting in the packet, and in IP over IP, it doesn't exist. In Ethernet over IP, the Ethernet header, including the VLAN and the user priority, is part of it. And this, of course, provides the ability to run some of the management tools that we previously mentioned. The second item is the compatibility with the L2-based applications. So Ethernet and Ethernet over IP will have seamless support for these applications, but IP over IP doesn't support them. And in last year, we presented a solution called EoIB over IP. It's a shim layer that provides para-visualization support for KVM. We also used it for VMware and Windows. And for EoIB over IP, we had to do some special handling for these L2-based applications. For example, ARP, DHCP, these kind of applications or protocols had to be handled in a special way to make EoIB over IP work. And in Ethernet over IP, these things would work seamlessly without touching the packet. And the third and fourth lines describe the MAC setting. The link layer setting in Ethernet is pretty flexible. So first of all, it's short, it's 6-byte MAC address, and it's flexible in a way that you can set any MAC address you want without any restrictions. But in IP over IP, the specification was designed in a way that the QP number and the GID as part of the layout. So whenever you want to set your own MAC address on IP over IP, that wouldn't work. And we had this problem especially with hypervisors, where the virtual machine has its own MAC address that the hypervisor provide, and to make the MAC address travel on the wire, IP over IP wouldn't be able to do that. And again, we presented last year the IP over IP solution for this purpose, but still the VM loses its identity the moment the packet travels on the wire, because the IP over IP wire protocol is still the same, and the MAC address would not be able to be customized in IP over IP. So with Ethernet over IP, the MAC length is standard, is 6 bytes MAC address, and the settings of the MAC address is also pretty flexible. You can have any MAC address you want. It doesn't really rely on any InfiniBand resources like the QP number or the GID. And as a result of these actually differences, the migration is one of the impacts or side effects from the Mac. So in hypervisors where the virtual machine can migrate from physical host A to physical host B, the network device, the native driver, doesn't need to do anything in Ethernet. The way it works is just whenever a virtual machine travels to a new place, it sends ARP or RAR packet, and this will teach the Ethernet switches in the wire on the network the new place of the virtual machine MAC address, and that's it. In IP over IP, this is not possible because IP over IP MAC address relies on the QPN and the GID, and the moment you have a new IP over IP interface on a new place, then you have a new MAC address. And to fix that, you need to tell all the neighbors that you have a new identity. So with Ethernet over IP, we designed the protocol in a way that there is nothing need to be done to make migration work. The same control plane that we use for the basic functionality would also include in it how migration is handled, similar to the way that Ethernet handles migration. The last two items for MTU and VLAN. So the MTU, since Ethernet over IP and IP over IP are overlay networks over InfiniBand fabric, they inherit the same physical restrictions in the InfiniBand characteristics like the MTU. So the MTU, for example, in Ethernet is defined to be 9K for jumbo frames, but for Ethernet over IP and IP over IP is still 4K in UD mode. So this doesn't change between IP over IP and Ethernet over IP. It's still the same because it's restricted or limited by the InfiniBand fabric. On the other hand, the VLAN identifier in Ethernet can be any value between 1 to 4K. And Ethernet over IP, it's also the same, but in IP over IP, it's limited to the number of the P keys. So if you're using IP over IP, so there is no VLAN, there's partition keys. So you can have a child interface with this partition key. If you're using EIP over IP, the one that we presented last year for virtualized environment, then you're going to have VLAN support, but it's limited to the number of the partition keys, which is normally 128 in most of the devices and the switches in the market, in the InfiniBand ones. So as you can see, Ethernet over IP was designed in a way that we learned from our mistakes in the past, and especially from IP over IP, and we tried to mimic the same behavior of the Ethernet interface. So we not only have an Ethernet interface, but also we provide the same solutions and the same management tools that used to run over Ethernet, and now they're supposed to run on Ethernet over IP without any tweaks or patches or a special administration. And we think that this is one of the main disadvantages or downsides of having IP over IP today. So we hope that Ethernet over IP will be a good extension or replacement for these things. So the model that is used for Ethernet over IP overlay network is by spanning a giant virtual Ethernet switch. I will refer to it as VES in these slides. So we have a giant virtual Ethernet switch that spans the InfiniBand fabric, and it mimics a physical switch with a dynamic number of virtual ports. So each one of the physical machines, each one of the endpoints, will be able to plug itself with a vPort to the VES. And the moment you have this vPort connected, you can run on top of it a virtual NIC. The virtual NIC have the same characteristics as a physical NIC. It can have multiple MACs, it can have multiple VLANs, and the moment this model is defined, we see it simplifies the way that Ethernet over IP can be used. So whatever you would do in Ethernet over InfiniBand, just ask yourself the same question, how you would do it on Ethernet. So in an Ethernet switch, you have number of physical ports, and you have number of NICs connected for each one of the ports. Here we have one giant virtual switch, so it's one single switch. And everything that was configured on Ethernet switch now is configured on top of the VES. The only difference is that this virtual switch can be run as distributed VES, meaning that sometimes the configuration that need to be done, there is no actual virtual switch that you can do like SSH to it and do some configuration. So you need to do this configuration on the vPort. For example, if the VES has a FDB table, a forwarding database table, then each one of the vPorts will hold an instance of that table instead of having one switch entity that holds the FDB. So these kind of differences may exist between Ethernet and Ethernet over IP, but it still share the same logics. And we think by adopting this approach, the same management tools and the same problems that were challenged and fixed and solved in the Ethernet world, we will inherit the same problems and solutions for Ethernet over InfiniBand. And this would make things much easier, especially when we notice that changing the management tools in the market is not that easy. So we better mimic the existing behavior in order to also inherit the solution that exists in the market. And Ethernet over IP was designed in this way. So here you can see in the diagram multiple hosts, each one of them. So there is one virtual Ethernet switch, one giant Ethernet switch that spans the InfiniBand fabric. And the vPort is part of the host. So you can have one vPort, you can have two vPorts, as in host 2 and host 3. On top of the vPorts, we connect a virtual NIC. And on top of the virtual NIC, you can have multiple MACs and VLANs. The same way a physical NIC would work on Ethernet world. Here you can see that the same host can have multiple vPorts. So if you have multiple InfiniBand ports, you can have one vPort on each one of them. Also, if you have one InfiniBand physical port, you can still have multiple vPorts on top of it. It's a virtualized environment. It's a virtualized model that you can mimic multiple ports on top of the VES, even if you have one InfiniBand physical port. And on host 3, I put an example of link aggregation. We can have, I'm going to explain it later in some of the slides. So you can have actually one VNIC on top of two vPorts, similar to the way you can run bonding today in Linux. Today in Linux, you can run the bonding driver, and you have one interface on top of two uplinks, ETH0 and ETH1. So Ethernet over IP was also designed to make link aggregation work by using the existing management tools like the bonding and the teaming drivers that exist today in Linux. Also, there is the equivalent for these in VMware and Windows, and we believe that also these tools would run the same way. So the packet frame is pretty straightforward. We have the Ethernet data and the Ethernet header as generated by the operating system. Nothing, we don't touch anything here. The moment that the packet travels to the vPort, that is usually managed by the network device, the NetDev, then we push the Ethernet over IP encapsulation header. So there's some information here like the version, the source and destination vPort identifiers that travel with the packet, and we push them in the vPort level. And the moment the packet reaches the HCA, the hardware, we push the standard InfiniBand header and the CRC, and Ethernet over IP is defined on top of the UD transport. So whatever exists on the UD transport headers in the InfiniBand, we also have them here without any changes. The only change here is the Ethernet over IP encapsulation header, and everything inside remains untouched. We don't really do anything to the inner packet. One of the differences that we made with this protocol compared to other ULPs that exist today is the address resolution. So the new things that we designed from day one for Ethernet over IP is that the Ethernet link layer MAC address is decoupled from the InfiniBand resources identifiers. And this connects to the table that I showed before with the QP number and the GID. So the MAC address doesn't rely on any resources in the InfiniBand fabric. So if you have a different QP numbers, different GID, different LED, it doesn't have any impact on the MAC address. The MAC address can be customized the way you want it. And this is a must for a virtualized environment where the hypervisor is responsible for the virtual machine's MAC address, and it expects the MAC address to travel on the wire. So any other approach wouldn't be the same. It wouldn't work seamlessly. And we think that address resolution and having the link layer decoupled from the underlying InfiniBand network is one of the main advantages in the address resolution protocol that is adopted in Ethernet over IP. The second item is the decoupling from the ARP and the NDP protocols. So IP over IP today relies heavily on the ARP in IPv4 and in NDP and IPv6. And this creates a lot of obstacles in managing the protocol. So for example, if somebody wants to use a static ARP entries, it's challenging in IP over IP. If somebody wants to send a notification to the control plane in IP over IP in a way that it doesn't fit in ARP or NDP, then we wouldn't be able to do it in IP over IP. So Ethernet over IP is decoupled from ARP and NDP, meaning that you can have your own address resolution protocol. You can have it statically configured or dynamically configured. That doesn't matter. The Ethernet over IP protocol doesn't rely on it. At the same time, it provides a replacement for it. It has its own control plane that, that is used to resolve the address between the Ethernet layer to the InfiniBand layer. And this not only decouples the protocol from ARP and NDP, but also it provides a way to carry informations or notifications in the network between endpoints without limiting ourselves to the format of the ARP or the NDP protocol that exists today. And we think that this will make it much easier for the current implementation, and it also will provide flexibility in the future to provide solution for challenges or problems that we may have that we don't know about yet. So decoupling from ARP and NDP is also one of the changes, the main changes in the address resolution. And the last thing is the learning mechanism. So since Ethernet over IB can run without a centralized manager, then we added a learning mechanism in the ingress path, similar to the VXLAN or GRE overlay networks, overlay protocols, where you can learn the incoming packets and build your own lookup table. So Ethernet over IP also adopt the same approach, and this also will provide flexibility in things in scenarios like migration and changing identity or machines that go down and up again. So the way it works is that each one of the virtual ports in the endpoint holds its own forwarding database. It refers to, in the slides, I refer to it as FDB table. And the FDB table tells you how to map eventually the MAC and VLAN from the Ethernet layer to the InfiniBand address handle. So this is the goal of the FDB table. And the way the FDB table is built is by listening to the incoming traffic and learning the MAC and VLAN mapping to the vPort ID. And later on, we can also use the control plane to map the vPort ID to the InfiniBand address. And in any stage, whenever we want to send a packet and the mapping is missing, then we can do some flooding. We can do flooding of we can flood the packet to all the endpoints and the network. So we keep the correctness of the protocol. In the meanwhile, we continue with the address resolution. Of course, this may have some downsides by flooding the packet in the network. And these disadvantages of flooding the packet that also, by the way, exist in VXLAN and other overlay networks. We can save these floodings when we have the FDB table put on each one of the endpoints in a managed way. So we can do it by using a centralized manager later on, or we can put it manually on similar to the static ARP, the way it's done in the host. So the way the protocol is defined so far is to use the flooding when the mapping is missing, and we can extend its behavior to be more deterministic and save the flooding phase once we have deterministic FDB table that is distributed to the endpoints. So here we can see in the first column we have the MAC and VLAN. This is the Ethernet layer key. After that, we in the egress packet flow, we map it to a vPort ID, and the vPort ID eventually map it to the QP number and the LED when using the UD transport. The vPort ID is actually can be seen as if you have a physical Ethernet switch, then you have a fixed number of ports, and each one of the ports has a number. So this number is actually the vPort ID in this protocol. So if you have an Ethernet switch and you want to put some configuration for port number 3, or you want to do some link aggregation between port number 3 and port number 4, so the vPort ID in Ethernet over IB will represent this kind of configuration. And the link aggregation feature is one of the main reasons why we have the vPort ID as part of the protocol. And we can see it also in this slide. So this is the scheme of the FDB table in each one of the endpoints. So you can see that in the overlay address, we have the MAC and VLAN. In the underlying address, we have the vPort ID that maps eventually to the physical address, which is the QPN and the LED. The GID is optional. It depends if there is InfiniBand routers on the way or not. So I'll put it here as optional. And you can see that in the first entry, the vPort ID is sitting behind two InfiniBand addresses. And this is when link aggregation is used. So for example, if you have an Ethernet switch and you have two ports that you want to aggregate them together for lag, in InfiniBand, we must have a way in Ethernet over IB to identify this case and to tell that the packet is coming from the same logical port. So we cannot use the QPN and the LED, and we cannot use the MAC and the VLAN because if you see an incoming packet carrying the same MAC and VLAN, then it doesn't necessarily mean that these two ports are acting as one logical port. So this is why we put in the middle the vPort ID, and the moment you have vPort ID mapping to multiple physical addresses, we know that this vPort ID is actually running in lag mode, and this MAC and VLAN can appear from any one of these physical addresses. And the construction of the FDB table is done in two steps. The first step is by learning the incoming traffic. So the moment we get a packet, we check the MAC and VLAN, and we mapped it to the vPort ID. So this is the same approach that a physical switch would work. So if in the physical switches, in physical Ethernet switches, for each port there is a table of the MAC addresses that the switch seen coming from that port. And so we do it the same way. We map the MAC VLAN with the vPort ID. And this will create the first column and the second column. And after that, we use the Ethernet over B control plane for vPort request and vPort reply to map the vPort ID to the InfiniBand address. And this actually will fill the last column. SA queries are still needed. So the moment we have the physical address for the QPN, LED, and GID, we still need to get the path record from the subnet administrator. So SA queries are still needed, and they're part of the protocol the same way any other UOP would need them. So this is an example of a way that ICMP ping would work with Ethernet over IB. In this example, there is ARP request and ARP reply, but we don't rely on them. I mean, if you're having a ping without ARP, that would also work. But in this example, we have like a realistic flow on how things would work on Ethernet over IP, where ARP request is a part of the flow. So on the left side, there's a VNIC and vPort. An easy way to look at it as two levels. So a network device can implement the two logical components, the VNIC and the vPort. And this one is the sender. This one is the receiver. So the moment you run ping from machine A to machine B, the first thing that happens is that ARP request is sent out if there is no resolution in the ARP table, in the ARP cache. So the moment ARP request is sent out, it's the first time it's sent to the broadcast domain. And it will be received by the vPort on the other side, and it will be forwarded to the VNIC layer. In this stage, the second machine, the receiver, would learn the MAC VLAN to the vPort mapping. So in the scheme that we've seen before here, in the first stage, we fill the MAC VLAN with the vPort ID because it's part of the packet. If the receiver, machine B, sees that the IP address in the ARP request corresponds to its configuration, it will answer with ARP reply. The ARP reply is usually sent as a unicast packet. So it's going to be sent from the VNIC layer to the vPort layer, and the ARP reply need to be sent here. But the FDB is incomplete because we have the vPort ID, but we don't have the InfiniBand address for it. So the moment there's incomplete entry in the FDB table, we just do flooding and we send the packet on the wire to all the endpoints. So the vPort on machine A would receive the packet and will forward it to the VNIC layer. At the same time, because we detected an incompleted entry that is being used, we send a vPort request asking for the InfiniBand address for the vPort ID that we're trying to use. This is a control packet, as you can see here in the explanation of each one of the rows. So the dotted line is the control packet, Ethernet over IP packet that is sent outside, and it's received by the vPort. The vPort here will detect that this vPort request has somebody is asking about its vPort ID, and it will send back its InfiniBand address. The moment the vPort reply is sent out, any ICMP or any unicast packet sent from this side to this side would also run as unicast packet because we have a complete entry. So actually, the moment we reach this point where the vPort request is received by the sender, then we learn the vPort to the InfiniBand address mapping. And following this stage, the driver is supposed to send an SA query to obtain the path record. So in this stage, the FDB entry is complete. We have MAC VLAN to vPort ID that was learned the moment we get the first packet. And the moment we want to talk with the destination, a viewport request was sent out, and we have the physical address mapped. Of course, we should have, like, theoretically, there is a fourth column for the path record that need to be obtained by the subnet administrator, and it's managed the same way it's managed today in IP over IB. So in this stage, we have the FDB entry complete, and from this point, any coming unicast packets would be sent to the destination without any control plane involved or without any flooding. So this is an example of how a ping would work, and how the FDB table would be constructed. I have some backup slides, so if you don't have, do you have any questions or, yeah?
Yeah, so go back to the slide. So why, the worst position should give you the QPN, lid, etc. on the sequence. Why not use that to, instead of saying you have to be complete, you get a query right there for the reply?
Yeah, we could do that. This is not InfiniBand spec compliant to learn the completion. Also, the moment you have some advanced features like TSS, transmit side scaling, where you have multiple QP numbers sending, so you're gonna get, I can create like millions of QP numbers. I can use any of them, and this is spec compliant. So if you want to learn the completion, you're gonna get some information that maybe not the information that I want you to send to me on them. So we thought about it, and we think that this mechanism is much more flexible and provides solution for future network device features such as TSS. Yep.
So from the enterprise side and from hosting, where do you see a security context entering this, or where does security fall into the admission of the Ethernet? How do I make sure I don't just invite myself to somebody else's VLAN, or is there some mechanism for assigning the vPort in a secure way, or that you trust that?
Yeah.
Since it's no longer the GUID you care about anymore at that point.
Okay, so anything in the Ethernet header and the Ethernet data, it's secured the same way it's secured in Ethernet. Okay, so MAC anti-spoofing, VLAN anti-spoofing, the same way it exists in Ethernet, it exists here. And current and future HCAs supposed to know how to peek into the packet in order to provide hardware security. But if you're using models like para-visualization models where the vSwitch would provide the security on that level. This is for the Ethernet header and beyond. For this part, that includes the vPort, there's two ways to secure it. The first way is to use the managed mode, meaning that the FDB table will be provided by a manager. Okay, so this is not what I explained in the slides, where we see that having unmanaged or distributed mode has more flexibility. But if you want to have the FDB table coming from a trusted entity, then you can tell, okay, this vPort ID is mapped to this lid and GID, and we can secure it in a way that we can ask the manager whether this entry is valid or not. If you're using a distributed mode, unmanaged mode, the way we think that vPort ID can be secured is by building the vPort layout to depend on the InfiniBand address. For example, if the vPort ID equals to the lid, and the lid is secure because nobody can change the lid as an untrusted virtual machine, then any receiver can check if the vPort ID is fake or not by peeking into the InfiniBand header and comparing the lid to the vPort that exists in the encapsulation header. So we have few approaches on how to secure the vPort ID. Having centralized manager is one of them. Having a secure vPort ID layout is one of them. And for anything else is the same way that Ethernet would secure it.
Oh, okay.
Hi, so I have 3 short questions. My first question is, what is the performance impact due to the encapsulation that you're doing?
The encapsulation is actually not the thing that we worry about. It's more the lookup tables. The encapsulation itself doesn't have any impact on the bandwidth, and the impact on latency is very minor. So for example, IP over IB already have the encapsulation header, and its performance is actually pretty good. Ethernet, for example, can provide VLAN insertion in the Ethernet header, and the impact for that is pretty minor. So in the encapsulation, we will not worry about it. We think that the bandwidth would be the same, and the latency would be pretty similar to a native InfiniBand packet. The lookup tables is something that would add to the latency the moment you have a large cluster. And we expect in the future the HCAs to be able to offload the lookup tables and overcome this problem. Still today, even with the existing protocols like VXLAN, the lookup table exists today in software. And we would have the same impact as other protocols. We don't introduce something new, but we also expect the future HCAs to be able to offload the lookup tables to the hardware and eliminate even this part.
So are you saying that, say for example, on an FDR, if you run Ethernet over IB, we would get similar latency and bandwidth numbers as I would get on native InfiniBand?
I didn't say as native InfiniBand.
Okay. How much is the impact? What I'm looking at is how much is the impact of running Ethernet over IB?
Yeah, so the answer for that doesn't connect directly to the Ethernet over IP protocol. It mainly connects to the TCP/IP overhead.
Okay.
Because even if you have the optimal encapsulation protocol on top of TCP/IP, and let's say that the encapsulation header is 0 and the lookup is a table of size 1, still the TCP/IP adds latency. So I would say that Ethernet over IP latency would be very similar to the Ethernet latency as long as we're using the same TCP/IP stack. And I don't expect it to be the same as the native InfiniBand. But there is a lot of efforts to improve the TCP/IP stack and to make it very, very close to the hardware. And we're gonna benefit from these improvements the same way any other network device would benefit from them.
Okay, so I guess you don't have any concrete numbers. So let me move on to my
We still don't
question.
have, it's still in phase of prototyping and
Okay,
defining
got
the
it.
protocol. We already have, we learned from IP over IB, and we learn also from other previous attempts for Ethernet over IB that we had in the past few years. And we know for sure that the bandwidth can be up to the wire speed. That's why I said the lookup table and the encapsulation doesn't really affect that. But in the latency side, we know that it's not as good as native, but it's still better than Ethernet. And the main difference or the main reason for this latency is the TCP/IP stack and not any of the parts mentioned in the protocols.
Okay, got it. So let me move on to the second question I had, is that have you, since you mentioned 802.1q, do you support the extensions that are needed for data center bridging?
Can you say it again?
The 802.1q support that you mentioned, would it also support the data center bridging extensions, for example, the 802.1.q, AU, AZ, BB?
Yeah,
so that you could run, and my third question is also similar to that, is that you could probably run fiber channel on it, FCOE.
Yeah.
I know it's just experimental from like, why would you want to do that over Ethernet over IB? But just from a concept point of view, would that work?
Yeah, so theoretically it can work, but actually I can answer you another question. Would DCBX would work on VXLAN or GRE or any other overlay network? It must have a meaning. So the DCB usually has impact on the physical characteristics. If you want the physical network to learn how to do congestion control or how to deal with the DCB or ETS or anything that you mentioned, then they don't have usually a meaning in the overlay network. They have a meaning in the underlying network. So for example, if you're running virtualized environment and you run VXLAN, okay, that has very similar logics, then there is no meaning in the DCB in the upper layers. You can run it and most likely it would work, but somebody needs to learn these attributes of the DCBX protocol or the DCB protocol and apply them to the hardware. And the hardware for the overlay network is virtual hardware. It's not the physical hardware.
Got it.
So even if they work in the protocol level, they don't have real meaning in the actual hardware.
So theoretically,
unless we do some mapping. And so far, we didn't see a reason to do this mapping because the InfiniBand network already have equivalent for these. And if you want to configure the physical network to have the equivalent of these protocols, then do it in the InfiniBand side, in the physical network side. You don't do it on the overlay network.
Okay, got it. Thank you.
Sure.
Any other questions? I'll take the shorter distance first. I'll be there. We haven't heard anything about multicast. How do you support multicast with this approach?
Yeah. Yeah, actually, I have a slide in the backup deck for the multicast. So the multicast is pretty straightforward. Each one of the multicast MAC addresses is mapped to multicast GID. So the equivalent for multicast in Ethernet is multicast GIDs in InfiniBand. So we defined as part of the protocol layout. It's pretty simple. It's very similar to the way IP over IP work. So you have you can have the PKey, VLAN, and the DMAG as part of the GID layout. And the moment you want to send a multicast packet from Ethernet, then we map it to the corresponding MGID according to this layout, and we just send the web packet outside. And also we, of course, defined well-known MGIDs for flooding, for broadcast, very similar to the way IP over IP works. So in this sense, there is no special handling.
Hi, two questions. The first one is, do you support jumbo frames?
So actually, we had this in this table. So today, when you have an overlay protocol, then it inherits the same characteristics as the physical network. In InfiniBand, today, jumbo frames is 4K MTU. Okay. There may be some attempt in the futures to make it bigger, but so far it's 4K MTU. And the moment you have Ethernet over IP or IP over IP or any other encapsulation protocol, then the jumbo frames for this protocol is 4K and not 9K. Okay, so this is one of the differences that we have between Ethernet over IP and Ethernet that we cannot overcome as long as we don't fix this or improve this in the underlying network.
So there are performance ramifications for that limitation?
We usually get to the wire speed, the InfiniBand wire speed, with 2K or even less than that. So we don't see, we know that the CPU utilization would be better using a larger NTU, but according to our experiments with Ethernet over IP and IP over IP, we reach the wire speed even with a small MTU. So we don't think that we would need it. The reason that we would like to have jumbo frames is actually for management, because the moment you have a bridge between Ethernet over IP and Ethernet, and you have some Ethernet hosts on the Ethernet side that has 9K jumbo frame, and they want to talk with the Ethernet over IP subnet, the packet may not work if you're using UDP. So it has impact on the management because somebody on the Ethernet side may be using an MTU that thought that it worked in this subnet, but it doesn't. But from the performance side, we're not worried about it. We think it's gonna be, we're gonna reach the wire speed even before 2K.
Okay, and the second question is, could you just sort of summarize the main reasons why a customer would choose E over IB versus just native E?
Performance. So today in the InfiniBand, you can have a FDR. You can have speeds that doesn't exist on the Ethernet fabric. And by running Ethernet over InfiniBand, you have the same look and feel as Ethernet. You can run sockets applications. You can run legacy management tools and protocols. And still, you can leverage the InfiniBand speed in bandwidth and latency. And not to mention the scalability and the pricing for InfiniBand and many other items that marketing people would know much better than me. Yeah, that's correct as long as we're comparing Ethernet over InfiniBand to Ethernet when running on the same TCP/IP stack. On the other hand, since Ethernet over InfiniBand can leverage the InfiniBand capabilities such as kernel bypassing, so actually in Mellanox we already have some products that can provide sockets API that bypasses the TCP/IP stack and provides a better latency. And this cannot be done the same way in Ethernet. In Ethernet, it needs some support in the hardware, and it already exists in InfiniBand. So as long as Ethernet over IP uses the same TCP/IP stack as Ethernet, then the latency would be very similar because most of the latency goes in the TCP/IP stack itself. But Ethernet over IP can leverage the InfiniBand VERB's ability to have kernel bypass and bypass the TCP/IP stack to provide a better latency, and this not necessarily exists in Ethernet. So on that side, we think that latency can be improved.
Okay, everybody, it's 6 o'clock, so I'll get one more question.
Thank you. I'm having a little difficulty in visualizing the overall stack that you're proposing. And do you have a slide which sort of shows how the overall stack looks like, and especially in the virtualized environment, because I think important motivation is to improve things like move vMotion and that kind of approaches. Do you have a slide, or maybe?
I don't have a slide. I can explain briefly, and we can talk offline about it.
Okay.
But I don't have a slide about it in this presentation.
Anybody else got a burning question? All right, the good point. Take it offline. So we're going to take about a 5-minute break before we do the general meeting. And again, everybody is welcome. It's right next door. We do have coffee and a few refreshments.
Thank you.
So please just give it 5 minutes. Thanks, everybody.